Hello everyone, I'm Fanyou and currently a postdoc at Purdue University. Today I will represent my team to give you a presentation of our solution to the Amazon KDD Cup. This work is done by me and my friend Yang, and the rest of the authors are our supervisors. Yang and I have won many champions and runner-ups for many competitions, and including the champions of the KDD Cup 2020. This year, we feel satisfied with the final ranking, although we lack some fortune to get first place in one track. Finally, we ranked 6th in task 1, 2nd in task 2, and 2nd in task 3. This competition is divided into 3 different tasks, which are named as Query Product Ranking T1, Multi-Classification Product Classification T2, and Product Substitute Identification T3. Task 1 aims at ranking the relevance of a subset of the dataset by using the NDCG score to measure the performance. Task 2 and Task 3 are either binary classification or multi-class classification problem and use the Michael F1 score, which are equivalent to the accuracy in this setting. So given this setting, it is natural to treat this problem into 2 tasks, Task 1 and Task 2, Task 3. In the following, I will use T1 to represent Task 1 and T2, T3 to represent Task 2 and Task 3. Next, I will try to do some data analysis. First, let us check the product catalog file. T1 and T2, T3 use different catalog table. Figure 2 shows the order of the product's entries in T2, T3. T1 remains a similar pattern unless it is started with Spanish entries. There is a part of products that have been used in both training and public test set, so we conject those entries are unique in the private test set. Let us have another investigation about the trend file. Figure 3 shows a histogram of the product grouped by the queries in T1 and T2, T3. Generally, most queries will sample either 16 or 14 products for training and test sets. And this distribution is slightly different between T1 and T2, T3, while we know that there are few exact labels in T1. So associated with those prior knowledge, using this product number as a feature to calibrate the prediction will make some improvement in the leaderboard. Another important information in the training set is that the proportion of the label in the T1 and T2, T3 are different. This difference creates a well-known data leakage for most participants that T2, T3, whether a query product pair is in T1 will improve the results in the T2, T3. However, it is not quite easy to use this information directly in the private test set. So, besides the above description deep dive, some other patterns will help to improve the scores as well. Here is a summary of those information. I have mentioned E1 and E2, E4 already before, so let's start with E5. So the product ID is called ASIN and will be identical to ISBN, which starts with digits if the product has ISBN. So ISBN are published contents, for example, like books or movies. So we designed a feature to check whether the product ID is ISBN or the ASBN or ISBN. E6, most query products groups has few unique brand numbers than products numbers, and the products with the most frequent brands tends to be labeled as exact. E7, at least one product in the query products group will be labeled as exact, and the label of the query product pair is affected by other labels in this group as well. Combining those observations, we could significantly improve scores for all 3 tasks, and I will introduce how to utilize them in the following section. So this figure shows our proposed solution for this competition. As we plan to attend all 3 tasks, for efficiency, we have to train the cross-encoders once and use them for all 3 tasks. This strategy makes this 2-stage solution the only choice. So we train all cross-encoder with all data from T1 and T2, T3 in 2 folds, and then combine the 4 class probabilities with other essential features, using light GBM to fuse those information and calibrate the prediction and finally adopt those results in different tasks. So in the first stage, we've applied the classical cross-encoders architecture with only minor modification. As the product context have multi-fields, we use neither the CLS token nor the min or max pooling to get the lantern vector of the query product pair. Instead, we conjugate the hidden states of predefined tokens. This small modification yield about 0.2% increase in the T2 public leaderboard. In the final solution, we ensemble 3 cross-encoders for each language that differs from pre-trained models, the trained data, or the input fields. For English entries, we used DEB RTA v3, Big Bird, and Coco LM, while for Japanese and Spanish, we used a multi-language version of the DEB RTA v3. All those pre-trained data could be found in the Hugging Face. While stating a lot of models have tiny improvement for both local and online tests, we start to do some feature engineering based on our observations. Combining E1, E2, and E3 together, we design a feature that measures the percentages of the product ID in task 1, product list grouped by query ID. This feature gives us about 0.5 percentage improvement in the T2 public leaderboard and remains effective for the private test set. And that's why we are extremely close to the first place in task 2. Based on E4, we use the product number for each query as a feature and obtain approximate 0.2% improvement in the task 2 public leaderboard. Based on E5, we designed features that measure whether the product ID is ISBN or not, and whether the query product group has an ISBN product or not. This feature gives us approximate 0.1 improvement in the T2 public leaderboard. Based on E6, we designed features that measure the unique number of brands in a query product group and whether the brand of the product is the most frequent one in the group. These features give us approximate 0.1 improvement in the T2 public leaderboard. Based on E7, we designed several statistics, mean, median, and max of the cross-encoders output probability grouped by the query ID. These features give us a 0.8 percentage improvement in the T2 public leaderboard. In the next stage, we send forecast probabilities from the cross-encoder models and those features to the LightGBM models. For task 1, we trained the LightGBM model with T1 data only to simulate the distribution and calculate expected gain by classification probabilities. For T2 and T3, we used all tasks from both T1 and T2, T3 to train either binary or multi-class classification model. So here is our milestone of public leaderboard for task 2. We use the red point and the blue point to represent improvement from the cross-encoder models or the gain from the feature engineering, respectively. We started to attend this competition about the 1st of July. With some efforts, we finally reached 0.831 for public leaderboard in the task 2. During the code submission round, the organizer proposed 120 minutes time limits for all 3 tasks. This time limits request us to provide more efficient solutions. We use knowledge destination to improve the model's performance. Knowledge destination is applied to English entries only. We use all data and train large version of DRBRT, AV3, Big Bird, and Coco LM. Then we use a linear combination loss of the cross entropy and the MSE loss. Here, we list some other inference accumulation strategies. So A1, we pre-process product token and save it as a H5 files. A2, we transfer all models to the ONNX with the FP16 precision. A3, we pre-sort the product ID to reduce the side impact of batch. We pre-sort the product by the number of tokens to reduce the side impacts of batch 0 padding. And the last one is that we use a relative small mini batch size which is equals to 4 when inference. We did a lot of local tests and finally find that small mini batch size, let's say 4 or 8, is optimized ones. So here's our solutions. You can find more details in my GitHub. Thank you so much.